Hello everybody, hope everyone is doing well. This is the first in a series of lectures aimed at, providing some online content for y'all since we're all separated at this point. I wanted to go over a couple of changes I made to the Canvas page and give y'all a clue at kind of how things are going to work here. This lecture will be from Monday's class, so it'll go up probably sometime between today. I'm recording this on Thursday and Saturday. It'll probably be up before the weekend starts. But I just wanted to give you a glimpse at kind of a couple of changes. First off is a change to office hours. If you've noticed here on the main page, I do have virtual office hours. And if you click on this link, it'll take you to a office hour waiting room, which is essentially, you can think of it as you go into this little online space. It notifies me you're in that space, and if you're the first person in line, I'll click on you and I'll bring you in to where we can chat face to face, virtually, and we can do I have a whiteboard, I can work on problems with you, whatever you need to do, and that will start next week on Monday from 1 to 3. So it is going to be a one-on-one thing, or if you have multiple people there with you, I could talk to all of them at once, but mostly just a one-on-one thing, kind of replicating office hours. But it will be virtual. So those will start next Monday, and they'll be 1 to 3 p.m. Monday through Thursday. I have posted a couple announcements here in the last couple of days that I wanted to make you aware of. The office hours, as I just discussed, but also textbook availability. I realize some of you have probably left campus, and if you're not planning on coming back to campus, you may or may not have remembered to take your textbook with you. So if you look at this textbook availability post, I do have a PDF copy of the textbook there available for you. I would encourage you not to share that with people outside the class. Copyright does apply to these sorts of things, and textbook publishers are being pretty lenient right now with everyone in this situation, but please don't post it online and share it with anybody. Other announcements. We will be scanning and uploading work. So if you go in and look at this particular announcement, I've given you some ideas for things that you can use to help you scan and upload things. Specifically, this is for quizzes. So normally we do quizzes in class on a paper, and I really want you to keep working on paper like this because it lets you show your work. It lets me figure out kind of what you know and don't know a lot better than, say, an online multiple choice quiz would do. So I am going to post quizzes just like we would have in class. I'll ask that you either download that to your iPad or print it off, then work through it and re-upload it. In order to re-upload it, you'll have to scan it though, and there are several ways to scan documents these days. Just scan it, save it as a PDF, and re-upload it to Canvas. Those will be due Friday nights at 11:59 each week. So the basic way the schedule is going to work is I will post lectures on Monday, Wednesday, Friday, and then you will have practice quizzes that'll be up at the beginning of each week with a quiz due at the end of each week. Your Maple quiz will be due at the end of each week as well. So those are the main things that you're looking at. Is basically you'll have 2 assignments due every week, and then when we have exams, we'll talk about exams once we get there. So that's kind of what we have going on at this point. There's really not a whole lot to add. All of the normal outlines and things like that we've been working on this semester, those will still be there. For instance, today in this lecture, we're looking at the eigenvalue eigenvector method. So if you go in, it still has all of the normal stuff with extra videos, links to Maple files that'll be useful to you on your Maple quizzes, and practice quiz 6 here on the front page. So normal stuff that we're going to be looking at here over the next couple of weeks. I will talk to you a little bit more about your presentations that'll be coming up here in about 2 weeks, or I guess 2.5 weeks. I'll talk to you more about those here coming up soon, but that's kind of where we are at this point. Most of these videos won't start with an introduction like this. I just wanted to take the time to make sure you were up to speed on some of the changes. What most of these videos will be is just a lecture video, and what you'll see is something very similar to this, where we're going to go through and I'm going to work some problems with you and talk about some things Like I would do normally in class, we won't have as many group activities or things like that we would do in class, but we still do have this lecture component that I wanted to talk about. So in particular, today's topic is we're looking at eigenvalues and eigenvectors, which for a lot of you is a new topic. So I'm going to try to introduce it as carefully and slowly as I can, while still needing to get through this pretty quickly, because this is a central part of the material for systems of linear differential equations that we've been looking at. So right before break, I believe it was maybe the Monday before break, we had looked at an egg boiling model. I don't know if y'all recall, but we had this egg that was trapped inside a 0-degree chamber. We had an egg yolk and an egg white. The water was held at 0 degrees. We derived it together, if you look back in your notes, and we came up with this system. So this was our egg boiling system. And the idea was, you heated the egg yolk, egg white up to a certain amount, then you let it cool off. We actually solved this system using substitution. If you remember, we used a sort of substitution elimination method to solve it. And we ended up with these component solutions. And I showed you at the time, since I was mostly interested in the form that the solution takes, I showed you how you can convert these component solutions to sort of a vector valued solution that I've shown below. And so while that substitution elimination method works, it's quite lengthy. It takes a good amount of time to do, and it's not very elegant mathematically. There's a far more elegant approach that'll reduce the time it takes for us to solve linear systems like this very, very quickly. What I will draw your attention to here is the fact that the solutions look like a vector times e raised to some value. In other words, the solution y of t that we end up with here is of the form c1 alpha 1 e to the lambda 1t plus c2 alpha 2 e to the lambda 2t. And the idea that this gives us to think about, at least, is under what circumstances is this equation a solution of our system. In other words, we have pretty good confirmation that this system did wind up being a linear combination of vector times exponentials. And what we'd like to do is we would like to find a lambda alpha pair that works. You can see for this example above, the lambda alpha pair that worked was here alpha's 1, 1/2, and lambda is -1. Those are paired together to form a solution to the system. Here, alpha is 1, -2. Those are its components, and lambda is -6. That pair forms together for a solution. So the idea is I want to plug this solution, alpha equal e to the lambda t, into our system. And if you go back up, this is our system, which if we rewrite that system, it can be written in the form dy dt equal, let's see here, the coefficient matrix is -2, 2, 2, and -5. So -2, 2, 2, and -5. So this is just a matrix form for that system, but I want to plug this in for y, and that's going to go in for y in two places. It's going to go in right here, and it's going to go in right here. So what does that look like? Well, you've got the derivative of alpha e to the lambda t is equal to -2, 2, 2, -5 alpha e to the lambda t. Now, for those of you that are more familiar with linear algebra, this will be slightly easier to explain some of this. For those of you that are less familiar, I'm going to try to go through all of the steps here. So we're differentiating alpha, which is this is just a vector of constants. So I can treat it like a constant when I differentiate and ignore it. So I'm looking at e to the lambda t, and the derivative of e to the lambda t is lambda e to the lambda t. So that's the derivative of the left-hand side. On the right-hand side, I have this matrix, which once again I can think of kind of like a constant here, but then I'm multiplying alpha, and let me write in some components here for alpha. Let's say the components, let's say alpha consists of components, let's say a1 and a2. Then this vector is a1, a2, e to the lambda t. Okay, I might as well do that on the left side as well. So alpha times lambda, this multiplication that I have here, lambda is a scalar value, so it would multiply by each component. So alpha times lambda would simply be a1 lambda, a2 lambda. So this is a1 lambda, a2 lambda, e to the lambda t equals, and then here I'm multiplying a matrix times a vector. So the way that you do that is, this is a 2 by 2 matrix. This is a 2 by 1 vector. The 2 in the front is the number of rows, and the 2 in the back is the number of columns. And you can only multiply these together if the inner numbers are the same. So the fact that those inner numbers are the same mean that we can multiply it together, and the result from multiplying it together is the outer numbers. So the result is going to be a 2 by 1 vector. So what this ends up looking like is you'll take negative 2 times a1 plus 2 times a2. That's the first component. And you'll take the second row times the vector, so you'll get 2a1 minus 5a2, that's the second component, times e to the lambda t. All right, not bad. So the next step at this point for me is to subtract this vector over. So let me move this over to the side, show you what I'm talking about here. Whoops, got a little too much. All right, let's move that over to the side. And what I want to do is take and I want to subtract this from both sides. So if I subtract that from both sides, what you have is negative 2a1 plus 2a2, 2a1 minus 5a2, this is a vector, times e to the lambda t, minus a1 lambda, a2 lambda, e to the lambda t. That would equal, doesn't equal 0. So this is one of the things that you need to be aware of. It doesn't actually equal 0 here. It equals the 0 vector. So this gives us this equation. And what you can see from this equation, let me see, I'm going to make all this a little bit smaller. What you can see from this equation is both terms have an e to the lambda t, which can be factored out. So you have a vector minus a vector times e to the lambda t. So what does the vector become? Well, it becomes minus 2 minus lambda a1 plus 2 a2. Right? All I'm doing is combining the a1 terms in the top component of the vector. And here I'm going to combine the a1 terms in the bottom component. And then the other term is minus 5. Let's see here. Oops. Minus 5, that's also minus lambda a2. So if I combine these two vectors, I can rewrite that left-hand side like this. Now, what I want you to observe here is something really interesting. If you look at this matrix and compare it with the original system matrix, the coefficient matrix, all this matrix is take the negative 2 and subtract lambda from it. Take the negative 5 and subtract lambda from it. That's where this matrix is coming from. So another way to write this is negative 2 minus lambda, 2 to negative 5 minus lambda, a1, a2, e to the lambda t is 0. So here's the thing. I want to solve this equation for a1, a2, and lambda. And there are only 2 equations here, but yet there are 3 unknowns. So there must be something about this situation that lets me determine one of these values, it's going to be lambda, so that I can use the equations themselves to figure out the other 2. So our goal here is going to be first find the lambda that works for this equation, then determine a1 and a2. So here's the thing. This is the system that we had. So one of the things that hopefully is very apparent about this, exponentials cannot be 0. This term can never be 0. So for any value of t. So if we're going to get the 0 vector out of this, this is the quantity that must equal 0. So this matrix times this vector right here must equal 0, 0, which is exactly what I have written right here. So this is that system that we just obtained. What's interesting to notice here is I could automatically always say that a1 equal a2 equal a0 solves this. The problem is that solution is called the trivial solution. It will always work. If you look here, that's tantamount to saying that a1, a2 is both 0. That's like saying alpha is 0, but I don't want alpha to be 0. I don't want that vector to be zeroed out because I'm assuming my solution is alpha times e to the lambda t. And if alpha were 0, then I would just be talking about the 0 solution, which we already know is an equilibrium point. We already know is a solution to these systems anyway. So for all of these 2x2 systems, 0, 0 is a solution, sure. It's just not the solution that we're looking for. The solution that we're looking for is something called a non-trivial solution. So this is where linear algebra comes into play, because if you take this system and rewrite it in its matrix form, this is minus 2 minus lambda, 2 minus 5 minus lambda, a1, a2 equal to 0. And so what we're essentially asking is, when does a matrix times a vector equal to 0 have non-trivial solutions? So when does this thing have non-trivial solutions? And that's a big part of linear algebra. So if you've taken the linear algebra course, this is called a homogeneous system, and homogeneous systems have non-trivial solutions. So this only occurs when the determinant of the matrix A is equal to 0. Now, there are several statements analogous to this. that you would talk about in a linear algebra course. Things like the columns of the matrix A are linearly dependent. You could talk about the row space of the matrix A, the null space of the matrix A. There are lots of analogous conditions or analogous statements to saying the determinant of that matrix is 0. But for us in this course, it's going to be easiest to talk about determinants. So I really need to know what the determinant of this matrix is. Well, if you have a matrix that's of the form A, B, C, D, let's say, so say this is our matrix A, then the determinant of that matrix is AD minus BC. It's this sort of cross multiplication. So AD minus BC. For us in the problem above, this is negative 2 minus lambda, negative 5 minus lambda, minus 2 times 2, which, let's FOIL this out. I get 10 plus 5 lambda plus 2 lambda plus lambda squared minus 4, or lambda squared plus 7 lambda plus 6. So the only time I get non-trivial solutions is when this determinant is 0. Here's the determinant. If I set it equal to 0, there are only two values of lambda which work. The two values of lambda which work are negative 6 and negative 1. And it's not surprising that that happened. If you recall, when we did substitution method, we came up with this equation as well in our notes. If you go back and look at them, this thing is called the characteristic equation of the system. And no matter how hard we try, if we want to solve this system, even with the method we used before spring break, we're going to come across that equation. It's characteristic, it's intrinsically baked into the mathematics of the system that we're trying to solve. And you may or may not recognize these two numbers. If you go back and look at the solution that we have here, let's go back up and look at our egg model solution here. The solution that we had before spring break, notice lambda negative 1, lambda equal negative 6. Those are the two lambda values that were in our solution. And this is where they are coming from. So the question is, okay, going back, we knew we were going to have to first find lambda. We've done that. And then determine A1 and A2. So how do I determine A1 and A2? Well, if you have our system here, this is the equation we're trying to solve. We know this system can only be solved for these values of lambda. And so let's put those values of lambda in. We'll start first with lambda equal to negative 6. If that's the case, then our system above, this system here, our system is negative 2 minus lambda, so it's negative 2 plus 6, which would be 4, and negative 5 plus 6, which would be 1. So this is what we end up needing to solve for A1 and A2. Notice, by the way, that these columns are linearly independent, which means that they are a constant multiple of one another. Column 1 is twice column 2. That must happen, or else the determinant wouldn't have been 0 in the first place. In other words, the reason that happened is because we plugged in this special value of lambda, negative 6 in this case, to make this occur. So you can immediately see the solution to this if I take, let's say, 1 times column 1 and negative 2 times column 2 and add those columns together. The result will be everything zeroes out. So the weight of column 1, well, that's A1. So A1 is 1. The weight of column 2 is A2. That's negative 2. So my solution, the alpha, so if this is lambda 1, the alpha that goes along with it has components 1, negative 2. And you can see that in the solution above here. Along with negative 6, the vector is 1, negative 2. So these values of lambda are called eigenvalues. And the corresponding vector associated with each eigenvalue is called the associated eigenvector. So we know from this that the solution that comes out of this relationship is 1, negative 2, e to the negative 6t is a solution. Okay, we find the other solution by plugging in the other eigenvalue, which is negative 1. So rather than adding 6 to each diagonal, I'm subtracting a negative 1. I'm adding 1 to each diagonal. So this will be, let's see here. You'll get negative 1 to, let's see, adding 1 there would be negative 4. So let's double check. Do we have a redundancy? Redundancy means is one column a multiple of another column. So if you look here, let's see, column 1. If I multiply column 1 by 2 and I multiply column 1 by 1, then add those each row down. So 2 times negative 1 plus 1 times 2, right? So 2 times this column plus 1 times this column, both things would zero out. So what we know here then is that alpha 2 equal 2, 1 are the weights of the columns needed to zero it out. This is the associated eigenvector. And so the solution in this case would be 2, 1 e to the minus t. And if you go back up to our egg model from last time, we don't get exactly the same thing. Notice you get 1, 1/2 here is what we got in class. And this answer is 2, 1. So if you compare 1, 1/2 versus 2, 1, notice that if you multiply this one by 2, you get the other one. In other words, the choice of eigenvector, and it really is a choice, is unique only up to scalar multiplication. In other words, if you have an eigenvector and I have an eigenvector and our eigenvectors are different for a given eigenvalue, then yours is some multiple of mine. That must always be the case. It's covered though, because remember we take a linear combination of the two. So if you have C1 times yours, then I have C1 times mine. Our C1s will end up being different, but our solutions will end up being the same. All right, we just learned a massive amount of linear algebra there in a very short time. I kind of wanted to go over a little bit of the terminology here to make sure that you understand some of the things we're going to be talking about in future lectures. The lambdas that we've been coming up with are called eigenvalues. They're the eigenvalues of the matrix A. So an eigenvalue is associated with matrix A if there's a non-trivial solution of this thing. So in other words, this is what we call the eigenvalue problem. This is the problem that you're always trying to solve. It's the problem that we solved above. Where did we have A alpha equal lambda alpha? Well, you can look right here. This is right here. Right, so this is lambda alpha. So this right here is lambda alpha equals the e to the lambda t's, those drop on both sides. This right here came from multiplying the matrix A times the vector alpha, so this is A alpha here. So right here, what we had was the eigenvalue problem that we were trying to solve. So A alpha equal lambda alpha is our eigenvalue problem. So if you have the eigenvalue problem in this form, all those manipulations that we did above simply mount to us doing this. We subtract this term over. then what you do at this point is realize that this lambda is really lambda times, because this is A. This is a matrix. Lambda is a scalar. So if I were to take out alpha, we would normally think of this as lambda times 1 times alpha, but in matrices, 1 is played by the role of something called the identity matrix. So this I here, in a 2 by 2 case, would be 1, 0, 0, 1, right? So that you have A minus lambda 0, 0, lambda times alpha equal the 0 vector. And so all this is this A minus lambda I. This is the original system matrix with lambda subtracted from the diagonals. So we obtained eigenvectors by solving this system. You can see it right above. This is A minus lambda I times alpha equal to 0. That's what we ended up solving. And so once we picked our lambdas, this is still A minus lambda I, but it's for that specific lambda 1. So that's the equation that we solve to come up with our eigenvectors, alpha equal A1 and A2. And we just learned that that equation can only be solved non-trivially if the determinant of that matrix is 0. And the determinant of that matrix ended up giving us this equation, this characteristic polynomial that we can't escape. For us, it was the lambda squared plus 7 lambda plus 6 equal to 0. That's what we had to solve. And what will always happen here is that the set of eigenvectors that we get will be linearly independent. So the two eigenvectors that we produced, 1, -2, and 2, 1, those are linearly independent of one another. I can't multiply this one by a constant and get the other one. If I did, then I did something wrong. But if you had, say, a 4 by 4 system instead of a 2 by 2 system, you'd get 4 eigenvectors, and all of the eigenvectors would be linearly independent when you do this method. They form a basis for what's called the eigenspace of the matrix. That's a linear algebra term. For us, they form a basis for the solution space. So we write our general solution in terms of these eigenvectors and eigenvalues. And one thing that often comes in handy if you're searching for the eigenvalues of a matrix, if the matrix is a triangular matrix, the eigenvalues can be found along its diagonal. For example, if you had the matrix, say, 1, 2, 5, 0, 3, -2, 0, 0, -5, if this is your system matrix A or your coefficient matrix, the eigenvalues of A would be 1, 3, and -5. You already know the eigenvalues because the matrix here only has values in that upper triangle, so we call this an upper triangular matrix. And from property 7 here, the eigenvalues of an upper triangular matrix always occur along the diagonal of that matrix. The same is true for a lower triangular matrix. So if you have an upper triangular or lower triangular matrix, it's very, very easy to read off the eigenvalues. So I know your head's probably spinning at this point. There's a lot of linear algebra terms I threw out at you. We're going to do a lot of examples of this to kind of get you up to speed with what these terms are. And then you can also use Maple to check your answers. I'm going to show you how to find eigenvalues and eigenvectors in Maple. So let's start with finding determinants. We know we're going to have to find the determinant of a matrix that looks like this, right? This is so suppose our coefficient matrix for our system is A, B, C, D. Then the matrix A minus lambda I is this. So this is the matrix that we're going to have to set A minus lambda I alpha equal to 0. This is the matrix that you're going to have to solve against A1, A2, to be able to find the eigenvalues. So I've got to know how to find the determinant of those matrices. As we did before, it's the diagonal times each other, so this times this, minus the off diagonal, so minus the off diagonal multiplied together. And if you do a little bit of algebra, you can group it this way. Now, what I want you to see here is the following. If you go back to the matrix A, the A plus D term that shows up right here is simply the sum of the main diagonal elements. We call that the trace of the matrix A. Its shorthand notation is TR of A, or trace of A. Similarly, you should recognize the value AD minus BC. AD minus BC is the determinant of A. So the point to this is, if you go back to our earlier work, so all this work that we did here isn't necessary. I can immediately find this guy. I can immediately find this guy from the original matrix A. And how do I find it? Well, I find it by calculating the trace of A and the determinant of A. And once I calculate the trace of A and the determinant of A, the characteristic equation, which gives me my eigenvalues, is given by that equation there. All right, so I want you to take a second to practice this. So if you want to pause the tape right here, see if you can figure out what the eigenvalues for this matrix are using this characteristic polynomial. All right, so I'm going to talk about the solution now. If you haven't paused it, please do so and work it out first. So here's the deal. The trace of this matrix is the sum of the diagonals, which is 1 plus 4, or 5. And the determinant of this matrix is the main diagonals multiplied together minus the off diagonals multiplied together. So the determinant here turns out to be 4 plus 2, which is 6. So using this formula, our characteristic equation is lambda squared plus, it is the opposite of the trace. Be very careful about that. I almost made a mistake. It's the opposite of the trace. Lambda squared minus 5 lambda plus 6. And we want to know where that's equal to 0 to be able to find the eigenvalues. So the eigenvalues are the zeros of the characteristic equation. All right, hopefully this factors. It looks like it would be what? Lambda minus 3 minus 2. So minus 3 minus 2 is minus 5. Negative 3 times negative 2 is positive 6. Yeah, so that's right. So our lambda 1 is 3, and our lambda 2 is 2. Those are my two eigenvalues. All right. What do I do if I have a 3 by 3 system? So a 3 by 3 system would have a coefficient matrix that looks like this. And we have this nice way of coming up with the characteristic polynomial here. All this characteristic polynomial is really the determinant of A set equal to 0. That's all this thing is. So I can do something similar with a 3 by 3, but I don't have the nice trace determinant form to use. But I do have a way of solving 3 by 3 determinants. You can see here, if I take my coefficient matrix, so ADG, BEH, CFI, and I add on the first two columns, so repeat column 1, repeat column 2. Then all of the downward facing diagonals are positive values subtracted from all the upward facing diagonals. So the determinant of the matrix A in this case would be the sum of AEI multiplied together plus BFI multiplied together plus CDH multiplied together. So that's the positive term. You add that term minus do all the upward diagonals, which would be CEG, AFH, and BDI. So that's how you find the determinant of a 3 by 3. It's one way to find the determinant of a 3 by 3. There's another way which is also particularly interesting. It's called the cofactor expansion method. So the cofactor expansion method, if my matrix A is A, B, C, D, E, F, G, H, I, then I can find the determinant of A by doing the following. I can create what are called pivots, and I can pivot along any row or any column. So I'm going to identify column 1 as my pivot. If column 1 is my pivot, then I'm going to take A times, what you'll do is you'll cross out all of the row and column in which A resides. So A resides in row 1, column 1, so cross that out, and then that will leave this 2 by 2 submatrix, which is EFHI. So you will multiply by the determinant of that submatrix. Now, if you enclose a matrix or an array like this with vertical lines, that's another way to write determinant. If you do brackets like that, then it's a matrix, or you could use parentheses. But if you enclose it with vertical bars, just like this, then that's determinant. All right, so let me back up a second because I don't want to mess up my matrix that I have over here too much. So those are my 3 pivots. So you can calculate A times the determinant of E, F, H, and I. And then it alternates in sign. So it's the first one's positive, then it's minus. The next pivot is D. And you have to go in order. You can't go A, then G, then D. You've got to go down or across from left to right or up to down. A, D, then G. So D times, if you look at D, if you cross through the row and column that D resides in, then the values that are left are B, C, H, and I, right? So you've got B, C, H, and I left. So those are going to be the determinant values we use here. So B, C, H, and I. And similarly, so you're alternating signs. The next one is positive. Your last pivot is G. And if you cross through the row and column that G resides in, then you'll end up with that top right 2 by 2, which is, let's see, so G will be multiplied by the determinant of B, C, H, B, C, E, and F. And we've already seen how easy it is to find 2 by 2 determinants. 2 by 2 determinants are A, in this case it would be E, I minus H, F minus D, B, I minus C, H plus G times B, F minus E, C. And I guarantee you, if you compare this with this, you will get the same value. So these are 2 different ways of calculating a 3 by 3 determinant. You can calculate them using this cross multiply method, where you join 2 extra columns, the first column and the second column, and then you do downward diagonals minus upward diagonals. Or you can create pivots across any column or any row and look at these are called the cofactors. Look at the determinants of the cofactors that are left to calculate it this way. So let's put that into practice. Here is a 3 by 3 matrix. And at this point, I want you to pause and try it yourself. Try to figure out the determinant of this matrix. All right, so if you haven't paused, please do so, but we're going to take a look at this. The determinant of the matrix A. And I'm going to do the cross multiply method. So we've got -5, 1, -2, 1, 4, 1. And I'm going to add on the first two columns. So I'll add the first column in again, and I'll add the second column. Okay, so we're going to do, so just reminding you of how this works, we're going to do downward diagonals minus upward diagonals. Okay. So, downward diagonals first. -5, -5, -1, plus 1, -4, -2, plus 4, 1, 1. So all of that minus this next one. So we're going to do upward diagonals. Upward diagonals are 4, -5, -2, -5, -4, 1. And looks like 1, 1, -1. Sometimes you can go a little cross-eyed looking at this, but hopefully we can keep everything straight. So I'm just going to multiply these together. -5, -5, -1, that's -25, plus 8, plus 4. Let's see, that's 10. It's 10 times 4 is 40, but it's minus, right? So minus 40. Plus 20, so minus 20. Minus, but minus a plus 1. It's really easy to make a mistake here. Minus 25 plus 13 minus 60. So minus 85 plus 13. I get minus 72, which thankfully is one of the answers, and that is correct. So the determinant of this matrix is -72. All right. So I want you to try this one now. Pause if you need to. What are the eigenvalues of A? All right. Gonna work it now. So if you haven't paused yet, please do so. This one's actually really easy. This is an upper triangular matrix, right? So we know that the eigenvalues are along the diagonal. So we know the eigenvalues are 1, 4, and 5. But to see why they are 1, 4, and 5, I want you to think about what the cofactor expansion of A minus lambda I would look like. So A minus lambda I is 1, 0, 0. You're subtracting lambda from the main diagonal terms. And we're supposed to find the determinant of A minus lambda I. That's what will give us the characteristic polynomial. So I need to find the determinant of this matrix if I want to figure out my eigenvalues. Well, if you think about cofactor expansion, that actually works wonderfully here, because in the cofactor expansion I can choose any row or column to be my pivot, and the pivots are the multipliers for each of these determinant calculations. And so if I have an entire row or column that has a lot of zeros in it, it's very easy to calculate the determinant that way. So if I pivot in column 1, then notice the determinant of this would be 1 times, if I cross through that, I get the 4, 2, 0, 5. Whoops, wrong matrix. That's not the matrix I'm taking the determinant of. You got to be very careful here. The matrix that I'm taking the determinant of is this one. So if I pivot here, cross through those, then what I end up getting is the only cofactor that matters is this first one, because the other two will be 0, right? The pivot here will be 0 times the determinant, 0 times the determinant. Only this one gives me something. And so I get 1 minus lambda times the determinant of this cofactor, which is 4 minus lambda 2, 0, 5 minus lambda. So that's the only thing that gives me anything here. Calculating the determinant, it's the main diagonal minus multiplying the off diagonal. And what you see here is it instantly comes out pre-factored. It's actually really nice if you have an upper or lower triangular matrix, you know that the eigenvalues are indeed the values along the diagonal. All right. So we've learned a little bit about eigenvalues and eigenvectors. Now it's time to take that knowledge and actually work a problem from start to finish. And you're going to see this goes very, very fast as long as we stick to 2x2 examples. So I want to solve this system using the method of finding eigenvalues and eigenvectors. And for our reference here, the system coefficient matrix will always be called A. And in order to find the characteristic equation, remember it's lambda squared minus the trace of A times lambda plus the determinant of A. So let me calculate off to the side here. The trace of A is the sum of the diagonals, which is 2. And the determinant of A is 1 times 1 minus 4 times 1, or negative 3. So this is lambda squared minus the trace plus the determinant. And so it factors into lambda minus 3, lambda plus 1. So I know for this problem, my eigenvalues are lambda 1 equal 3, lambda 2 equal negative 1. And so what I need to do now is find the associated eigenvectors. Remember, the eigenvectors come from solving. So the eigenvectors solve A minus lambda I times alpha equal 0. So the easiest way to know how to do this is to take that coefficient matrix A, subtract lambda from the diagonal, so 1 minus lambda, 1 minus lambda. Do that for each of these, and then find the value of alpha. Remember, alpha here is just, say, components A1 and A2. Find the values of the eigenvector alpha that associate with the eigenvalue. In this case, we'll start with 3. So, case 1, lambda 1 is 3. Then A minus lambda I alpha would be 1 minus 3, 1, 4, 1 minus 3. Alpha is A1, A2 equal 0, 0. So this would be 1 minus 3 is negative 2, negative 2. We want to double check, is this column a multiple of this column? Yes, if you take 2 times the second column, you get the first column. And if you want to solve this, you need to look at the weighting here. So the weighting means if you multiply if you multiply 1 by this column and 2 by this column, and you add them together, that will zero out each row. 1 times negative 2, right? 1 times negative 2 plus 2 times 1 equals 0. 4 times 1 plus negative 2 times 2 equals 0. That tells you your eigenvector. Your eigenvector is the weighting of those columns. So your alpha vector is 1 for A1, 2 for A2. If you have trouble understanding what I just did there, it might be helpful for some of you to think of it this way. Write it in system form. Minus 2A1 plus A2 equals 0. 4A1 minus 2A2 equals 0. That's the system form. And then just pick any value of A1 you want. For instance, if I set A1 to be 1, then I've got minus 2 plus A2 is 0. And 4 minus 2A2 is 0. And that in that case, that would automatically imply that A2 has to be 2. And it actually is the same for both because the two columns are dependent on each other. So A1 would be 1, A2 would be 2, which gives me 1, 2 like I have here. That will always happen, that those will equal each other because of the way that we've chosen the eigenvalues. So alpha is 1, 2, is our associated, so this would be alpha 1, is our associated eigenvector for lambda 1, which is 3. All right, case 2, lambda 2 is negative 1. And so we have A minus lambda I. Alpha would be subtract 1 from the diagonal. So 1 minus negative 1. 1 minus negative 1. So that would be 2, 1, 4, 2. Check once again and see, are these columns linearly dependent? Yeah, if I take, let's see, if I take negative 2 times this column and 1 times that column, that works. That will zero everything out. So alpha 2 is 1, negative 2. And notice that these look close to each other, but these are not multiples of each other. So these are actually linearly, what we say, linearly independent. Linearly independent eigenvectors. So once you have that information, you can form a general solution. The general solution to the system is C1 alpha 1 e to the lambda 1t, just like it was for that egg boiling problem. C2 alpha 2 e to the lambda 2t, which in our case would be C1, let's see, alpha 1 is 1, 2. Lambda 1 was 3. Alpha 2 is 1, negative 2. And lambda 2 is negative 1. So there's your general solution. We wanted to solve for specifically 3, 2. So if you look, y of 0 equal to 3, 2, that's my initial condition, right? So this is my initial condition. This is what's going to let me solve for C1, C2 to find a particular solution. So I can find the particular solution by setting y of 0. So y of 0 would be C1, 1, 2, C2, 1, negative 2. I'm going to set that equal to, let's see, y naught was 3, 2. I'm going to set that equal to the initial vector 3, 2. So this ends up giving me a system C1 plus C2 equal 3, 2C1 minus 2C2 equal 2. And we'll solve this system in the usual way. Elimination is my preferred way. So you can multiply this top equation by 2 and add it to the bottom equation, and notice that that will eliminate the C2 term. So you get 2C1 plus 2C1, which is 4C1, equal 2 times 3 is 6, plus 2 is 8. And then those will cancel. So C1 would be equal to 8 divided by 4 is 2, which would then force C2 to be 1. Because the first equation is C1 plus C2 is 3, so C1's 2, C2 is 1 to give 2 plus 1 equal 3. So I know the values of C1 and C2 in this problem, which means I know the particular solution. So the particular solution in this case is 2, 1, 2 e to the 3t plus 1, 1, negative 2, e to the negative t. And there are many different ways to write your answer at this point. I actually like the component form. So if you read across the top row, you get 2 e to the 3t plus e to the negative t. If you read across the bottom row, you get 4 e to the 3t minus 2 e to the negative t. So this is what your x coordinate is doing. This is what your y coordinate is doing. So that would be a solution to this problem with the 2x2 example. The 3x3 example, I'm going to leave for y'all to try to do this one. I will mention that you should probably try cofactor expansion here. So in other words, your matrix A minus lambda I would be 1 minus lambda, 1, 2, 0, 2 minus lambda, 2, minus 1, 1, 3 minus lambda. So I would recommend finding the determinant of A minus lambda I. I want you to do it using cofactor. Right? So if you use a cofactor expansion, this is going to be one minus lambda times this determinant. Notice that the next pivot is 0, which zeroes out the negative term. So the third term is negative 1 times, and its cofactor will be this. So you can use that to define the determinant, which will then give you the eigenvalues, which will then give you the eigenvectors, and you can put the solution together in that form. All right, I want to go now and take a look at something in Maple with you. So let's jog out of here real quick. All right, so you have access to this Maple file online right now. I just wanted to show you a couple of the Maple commands. These will be useful, and all the things we'll talk about this week will be useful for your Maple quiz that's due on Friday of next week, March 27th. Entering a matrix in Maple is actually a pretty easy thing to do. We've done this already this semester, but you see we've got the matrix here, 2, negative 1, 2, 5. That comes from this column palette over here for matrices. You can define how many rows you want, how many columns you want, and then just insert matrix. For example, if I was to do it for this one, so I've got A colon equal. Okay, so I'm going to define the matrix A. It's a 2x2 matrix. I'm going to define it as 2. Tab is the best thing to use to get from spot to spot. So 2 tab negative 1, tab 2, tab 5. And so there's my matrix A. And now all I have to do if I want to get eigenvalues, eigenvectors, stuff like that, is click on the matrix. And you see over here to the side, it's got characteristic polynomial, eigenvalues, and eigenvectors. And I show you what each of those commands give in the worksheet. So you can get the characteristic polynomial, the eigenvalues, and the eigenvectors real easily. I want to make sure you understand how to read this form. The two eigenvalues are 4 and 3. So if the eigenvalue is 4, that's the first component here. It corresponds to the first column over here. So 4 as the eigenvalue has eigenvector negative 1/2 and 1. 3 as the eigenvalue has eigenvector negative 1, 1. So the first row here corresponds to the first column here. Second row corresponds to the second column. And you can see then that the general solution would be C1 times the first column e to the first eigenvalue plus C2 times the second column e to the second eigenvalue. You can also do this with a 3x3, and I'll show you an alternative way rather than just right-clicking on the matrix. If you enter the matrix here, I have a 3 by 3 entered. I can right click and get the characteristic polynomial just to show you if you solve that equal to 0 for lambda, that does give you the eigenvalues. So you can just solve the characteristic equation equal to 0 for the eigenvalues. But if you load the linear algebra package, rather than right clicking on the matrix, you can just say what are the eigenvalues of the matrix A, and it lists them. Here you can say what are the eigenvectors of the matrix A, and it lists them. It's still the same thing as above, where this is the first eigenvalue. So this is the first eigenvalue in row 1. And if you look at column 1, that's the first eigenvector. Eigenvalue number 2 is negative 2i. Its eigenvector is second column here, 1/2 minus I over 2, minus 1 and 1. Be very careful. The imaginary I that they use is capital I, and it looks a lot like the 1. So just be very careful about that. I then have a general solution here. I'm not going to go too much into that in this lecture because it does involve complex eigenvalues, which we'll talk about in Wednesday's lecture. But I do want you to know that you have access to Maple to use on this, and that we will actually look at solving some of these systems in Maple and comparing some of the stuff that we've talked about today. All right, it's been kind of long. Some of these lectures will be kind of long, but you can pause and come back to it at any part. We'll do another lecture like this on Wednesday and start looking at more and more material. If you are kind of wondering where we are in the textbook at this point, if you want to keep up, most of the information that we've talked about here in today's lecture stems from section 3.1 through, I would say, 3.3. So we covered, mostly 3 sections today. I would recommend that you read those sections first. So read those sections first. Then I would probably, after that, I would probably tell you to watch some of the videos that I've posted on the section 3.1 to 3.3 page. So watch videos and take notes. And then there are lots of practice problems in the textbook that you could look at. There's also going to be a practice quiz that'll be up relatively soon. You can look at that. And then just start working on the quiz and the Maple quiz. And if you have questions, let me know. All right, y'all have a good week. I'll see y'all again on Wednesday.